Good afternoon. Welcome to Krishna's class. We were exploring the structure of L infinity x. Sorry, LPx for 1 less than or equal to p less than. So we have structure of LP infinity. And we have proved that two things. One, LP is complete and CCX is space. Then CCX is dense in for 1 and in particular we looked at the special case RK, which often appears in the applications, especially while working on partial differential equations. And then all these results could be translated to that. Therefore, consequently, with Lebesgue measure, okay, is complete and LPRK for 1 and you see that it's interesting to look at the cases n equal to k equal to 1 and k equal to 2 often applications. For instance, we shall look at the case for p equal to 1. We take, then you are talking about L1 R p equal to 1 We take so that you are working on L1. So we have for F, G, L1R, we have OM1 integral over R1, that is from minus infinity to infinity. Mod F dV. And this, of course, doing all sorts of things like, therefore, the corresponding D1 so here L1 is not just the functions for which this is finite alone, but you see that here F is equal to G that is D1 Fg equal to 0 implies almost now this is the important point. It's not that the functions are identical. So this is the problem. Therefore, we resort to our technique of introducing what are called equivalence classes. So we introduce relation on the basic set of functions, and eventually by looking at the equivalence classes and then once again introduce on it, we see that with L1R denoting the space of equivalence classes of functions. I very elaborately considered this situation. The corresponding FTDT is no. Consequently, the corresponding D1 is a metric. So the corresponding D1 is a where of course the zero element is f is or then it is a metric, and therefore this is a L1 is a metric space, and L1R is L1R is denoting the space of equivalence classes of functions under the equivalence relation, that is f is related to g equal to 0. This is the equivalence relation. Okay. Otherwise, you can easily see that this integral, because you are defining it through the integral, you see that norm 1 of f as defined here is equal to 0 only means f is equal to 0 almost everywhere. You cannot conclude that f is identically equal to 0. That is why we do all this exercise and come up to this. But we are using the same notation for L1 tilde, which I have still. So let us just recall. Now, what more you can prove is this. Now you take CCR. That is, which consists of f complex value continuous functions with compact support so we are basically essentially talking about continuous functions. Okay, now you can clearly see that it's a subspace of L1. This is what you can immediately conclude. Can you say anything more than that? This is the question that you have. And from what you have said is, now you see, the functions are all continuous functions. For each function, there is a support which is a compact subset of R. So only on that compact subset, the function is not equal to 0. Outside which the function is identically equal to 0. At the same time, it is continuous. Okay, something like this. See, you have identically 0 here, identically 0 here, in between, something like this, sort of this. And it could be 0 at some points also. But there is a compact set outside which, on the complement of which, this function is equal to 0. So that the integral is essentially on this compact set. Now you know that on R or Rk even, the compact sets are, compactness is closed and boundedness. Closeness and boundedness. Do that way. That is the equivalent form of compactness on RT. It's a beautiful theorem. Okay, right? So that's the characterization of compactness. And therefore, what happens is, if you look at this integral, okay, this integral is finite. For any f belonging to CCR, you see that this integral is finite. Because this integral lives only on a compact subset or a bounded set, and further this is a continuous function bounded on the interval minus infinity to plus infinity, and with compact support. Therefore, the function is, there exists an m such that mod f is less than or equal, where m is finite, and therefore this integral is always finite. So this is well defined. So on CCX, because of the compactness of RK, and we are considering only functions in CCR, this is well defined. So there is no problem. Another point that you have to look at is this. See, we said that in L1R, D1 Fg equal to 0 implies F is equal to G almost everywhere. Suppose you confine yourself to the continuous functions with additional property of continuity for F and G. Then what happens is, norm of F minus G 1 equal to 0 if and only if F is equal to G everywhere, not almost everywhere. Okay. So CCR identical. Not F is equal to 0, almost everywhere. Therefore, you see, accordingly, all these things do work. Okay. Now, what we then obtain is this completion of this. So, in this case, completion of CCR is L1. So, that's the result that you have. Now, you see, similar situation arises in L2. But there is one additional interesting feature that L2 has. L2 is he is a Hilbert space, namely it is complete normed complete inner product space, which is modeled on our RK with the usual norm that you take. Okay, that means you have here and the inner product that you have is this is the inner product that you have. G conjugate. This is conjugate. Okay, this is the inner product. Just like the dot product that we have, this is the dot product of L. So you have the length coming out from there. That's very easy to see. And you see that again you have nice results like L2 is complete. And these are all very easy to argue and get. Okay, so we'll just leave it at that. And we have actually given the interpretation of our results for this particular case. Forgotten to put the date. That doesn't matter. Okay. So you see, these are the three extreme cases. See, when you consider 1 to infinity, the interesting cases are p equal to 1, p equal to 2, and p equal to infinity. These three are fascinating cases. The extreme cases, and this, of course, corresponding to the case where LP becomes a inner product space, and it's a complete inner product space. Therefore, it's a Hilbert space. So these are all Banach spaces, and of course, this we will examine. We have not said that these two are Banach spaces, and the additional structure that this particular P equal to 2 has is that it is it's a Hilbert space. It's an inner space. Okay, so we now look at the other extreme case. So our theme for this lecture is, so P equal to This is the one that we are interested in. So we consider what are called n infinity. Okay. So in this context, it is worthwhile to recall that every normed linear space has a completion. Every metric space has a completion. So just before going into this, we recall every normed linear space has a completion. And every metric space has means if S is a metric space, there exists a star such that S was a star is okay. That means this is embedded in a star where a star is uniquely. Now this needs some explanation. When you start with an abstract metric space, there exists a uniquely determined a star, and the uniqueness in the sense that any two distinctly appearing completions of now I'll put an arrow here to indicate that S is embedded. So if you have S1 star and S2 star, two such completions, then there is a equivalence. Sorry, there is a there's a isomorphism between S and star. That's the meaning. This if the star and S double star are two completions, Yes. So structurally, as matrix spaces, the two are identical, and S is embedded in S star. S also could be embedded in star because you can define a map. You can use this homeomorphism. So there is no problem. S is embedded in S star means every corresponding to every element in S, you can find a corresponding element in S star. At the same time, S star is not equal to S in general. Okay, right? So you have S here, S star here, S double star here. This is F. Now you have a replica of S here. So there is a replica of S here also obtained by a one-to-one into continuous map. Okay. And this may not be the whole stuff. And therefore, to see that you can through this actually you have a homeomorphism from here to. So using that you can find out what exactly is the image of a star. Okay, and get psi. Right? So that's easy to work out. So this is the homomorphism. Psi chi is the homeomorphism. Therefore, you see that psi is essentially equal to this is the relation. This is the relation. Okay. So that's just we are digressing from the main theme, but all relevant stuff only. So let us return to our problem. So we can now take the case. Infinity. Now what we have proved is that L infinity this we have proved in general. It is complete. But is CCRT dense What is, oh, okay, what is the norm on this? Meanwhile, note that meanwhile, norm of f infinity, essential supremum of RK. Okay, so we shall look at CCR. See, one of the important results that you can prove here is that CCRK. So the closure of CCRK, this is equal to, what is C naught RK? C naught RK consists of all those F which dies down. Okay. So C naught RK the set of all F continuous on RK with the property that F tends to 0, okay, we will make a more general statement that we can make instead of RK with X, and if you interpret it, this will turn out to be X. So we shall look at what one can do is comes out. which is not instance for this case, for instance, to consider then limit equal to 0. Of course, it's continuous. That's the meaning of that. And these are functions with compact sum. So you see that CCRK is in fact contained in okay, but they are not equal, right? This is something that you can say that, and they are not. That means there exist elements in C0 RK which are not CCRK. Okay, and you can see that, for instance, you take on R identically one function. Okay, does it have a finite now? Yes. You take L infinity now, then this is going to be supremum of fx for x belonging to R. And you see that fx is identically equal to 1. Therefore, supremum of fx is equal to, so let us consider. So, identically equal. Fx identically equal to 1. Consider then because the sup norm is equal to 1, which is finite. Okay, but f does not belong to C0 infinity or C0 because the function does not die down to 0 at infinity. And you can also see the function defined by, say, the following. Consider the function g and equal to 0. For example, you take the function, say equal to square not 0 I will gx equal to 1 for x belonging to, and this is equal to 1 upon mod x. Complement that. That means I'll do a completion from the quotation. Then G belongs to infinity. This is C naught R. So this is in C naught. But you cannot find a compact subset outside which, so there does not exist a compact set. So that's the example thing. Okay. So they are different. So what I wanted to say is that LCC this is the result. Okay. Now let us consider make the general consideration. So we need some new definitions. So we take x to be out of space, and then by a positive linear function on CCX. Okay, so you have now x. Example is that's an example. So we make a definition. We have to say what do we mean by C naught? On Rk, of course, you know that as mod x tends to infinity, the function goes to 0. You cannot make such a statement here. So make a statement on this because x is taken as a locally compact expression. A complex function f on a compact x is said to vanish This is a what you call a kind of a very decorative expression. There is don't know what exactly is infinity. So here, but our experience of working on RK, you are talking about point at infinity. Okay, that's why this terminology comes from that. Although in a general X, we don't know what exactly you mean by infinity. Okay, if to every epsilon positive there exists a compact set K contained in X such that mod fx is less than epsilon not belonging. That means in the complement of K, the function is as small as you please. So suppose this is your X, then what it says is, suppose epsilon is given, f epsilon are given, then you see there is some K compact such that in this part if you choose another epsilon, there is a corresponding K. So this K actually depends on epsilon. Now I give it a small exercise. Verify that this is equivalent to as mod x tends to infinity on that's a till exercise that you can do. Okay, you have to give a perfect rigorous mathematical argument to identify these two statements. Okay, or in other words, what I wanted to say is that you are trying to get the equivalent of this statement on a locally compact Hausdorff space. Then how you have to modify this? Simply says that given in epsilon positive, there exists some compact set outside which the function is less than, that is modulus of fx is less than epsilon. So if you choose a smaller epsilon, you get another compact set. So this compact set is fully dependent on what epsilon you choose. Okay, given f. So we make some remarks. All continuous function at infinity. And this collection we have already said C dot. So you see this is the equivalent of the root of functions. Further, is a proper subset of C naught x. Okay, then you can easily construct an example where an element of C naught x is not. In some cases they would be equal, because when this is going to be equal, side go inside if X is compact. For example, to take these two cases, okay, for example, you take x to be equal to in this case that is C0, okay, right? But suppose the open interval 0, then this is not compact. So here this is compact. So this is not compact. Then CC is not equal. So these are the two examples which will give some insight in what we have said. So in such cases, it's denoted by Cx or continuous functions. Okay, so now we prove the following. Housed of space is the completion of we have seen an example where C naught x may not be L1x. That we have already seen with the case x is equal to Rk, right? Then with L infinity now, this is the case. So they are taking. And the corresponding. Relative to the metric defined by the suit norm namely it is essentially supremum in fact, and essentially supremum in the case of continuous functions become supremum. So this is the theorem that we are going to do. So that means in L infinity now we are working out these things. Okay. So we give the proof. Proof is simple. We take C naught x d infinity, where that is the essential supremum of this. Is essentially in this case it is the supremum of this. This is a metric. One C naught x. Now we show the following. Following. The first thing that we prove is C naught x. CCX is dense in C naught x. The second statement that we prove is complete normally linear space. So this is the statement of the theorem, or this is what we are going to prove. Let me just work on case 1, that is A. C naught x and epsilon positive, where x is, because it is an element of C naught x, and we use the general definition, a compact set K such that Fx outside, that is on the complement of K, this is less than epsilon. Now what we do is the following. Okay, we appeal to a very useful result in topology, This is called the Urizon's lemma. So by Urizon's lemma, there exists a function G belonging to X such that less than or equal to 1 and for X belonging to K, Gx equal to 1. So the scenario is this. This is your X, this is your K, this is compact. So you have a function G identically equal to 1 and there is a support for this. So this is okay. Some compact subset such that G lies between and over here G is identically equal to 0. So outside this G is identically equal to 0. Now it's very easy to understand what is happening. See, you take the following case. Take X to be the open interval 0 to 1. So this is okay. Now suppose K is AB where what? So it is some like this. Now what we do is the G that you define is as follows. See, on this is your K on which you find G to be equal to 1. And then you have a is continuously patched up so that you see goes to infinity as x tends to 0 and x tends to 1. Okay, so this is the case. So on K the function is taken as 1 and there is some K1. So call this say, so you have K1 then AB is compact, AB is properly contained B1 on and G is taken as identically equal to 1 on AB. G is equal to 0 on A1, B1 complement. Okay. which is equal to CO2 A1 union on this, and G and 0 less than or equal to G. That means the support of A1 B1. This is the scenario that you have. Okay. Now similar things pushed across the general setup I have marked here. So that is the situation. Now let us, we have chosen such a C. Now define so the support of H is actually equal to the support of G, okay, or contained in support of G, right? So support of this is the situation, and these are continuous functions. H is continuous. Being the product of two continuous functions. Okay. Further, minus H and this is of course less than. What is the reason? Outside the support of H, okay, what you get is that H is equal to 0. Therefore, it is norm infinity of H, which is already less than H. So this is because therefore H has the property that therefore H belongs to CCX. Okay. So you have actually constructed, given F, you have constructed an H which is in CCX. So that is the first part. Now we prove B. B, the claim is C naught x is complete. So let A Cauchy sequencing this is the point-wise convergence that we are talking about because it's a Cauchy sequence. The reason is that less than epsilon. Given epsilon positive, therefore this is a Cauchy sequence. That means so thereby defining but this is uniformly Cauchy implies the limiting function is this implies it's a continuous function. Now the question that you have to answer is what we prove that there exists an N such that norm of N and there exists a compact set K such that mod Fn x less than epsilon by 2 outside K. Finance inside. Consequently, what you can immediately show is that what affects is and this is less than epsilon by 2. Outside, which implies vanishes that is f belongs to. So that completes the proof of this. So that is C naught x is complete. So what we have proved in the first stage is that CCX is dense in C naught x and C naught x is complete. Therefore, C naught x is the completion of C naught x. So that completes the proof. Okay, so we shall conclude this lecture here, and then possibly we may just look at what all things we have proved on L infinity. A very short lecture, maybe tomorrow also. Thank you very much. I will stop.